Hello everyone. In this video we're going to learn what an exponent is, and then we're also going to explore two important rules which apply to powers and exponents. The first one being the product rule for exponents, and the second one the power rule for exponents. Now if you recall, multiplication is nothing but repeated addition. For example, when we write 3 times 2, that just means 2 added in this manner 3 times to give us 6. Now, exponentiation in turn is repeated multiplication. So it's the next level up. As far as operational priority goes. And for example, if I write 2 and 3 slightly higher than it and slightly smaller, this notation here, we read it as the third power of 2 or 2 cubed. And what that means is basically use this number here, which is called the base, in a product 3 times as a factor. So then we just multiply it out. So we see that 2 cubed is just going to be 2 times 2 times 2, which is 8. A very common error that many students make when they first learn about exponents is they multiply the base and the exponent, which is completely wrong, of course. There is no scenario in mathematics where you multiply a base and an exponent. You have to interpret what the exponent means and then apply it. So make sure you never multiply the base and the exponent in what is called a power. So again, if we look at the general format here, we see that x to the n means x times x times x. We continue going till we have exactly n factors of x. So that's what the expression x to the n means. And x here is called the base of the power x to the n. N is the exponent of the power. And x to the n, of course, itself is the nth power of x. Sometimes people confuse powers and exponents. Power is the entire expression here. So this we call a power. The n is simply the exponent. For our first example, we're going to evaluate each of these powers. Of course, 2 to the 4 simply means 2 times 2 times 2 times 2. We have 4 factors of 2, and we multiply. So, of course, that's 4 and that's 4, so we get 4 times 4, which is 16. Now, in this first example, 2 is the base. And the exponent is 4. In our next example, the base is -2. And the exponent is 4 again. So what we're going to use as a factor 4 times in a product is going to be -2. So we have -2 times -2 times -2 times -2. Of course, these two negatives, when we multiply them, give us a positive, and these two also give us a positive. So we know the overall answer is going to be positive. So when it comes to a product, the easiest way to tell the final result, if of course you have only multiplication involved here, is to count the number of negative factors. If that number is even, we're always going to get a positive answer. Even if we have some positive factors in there, it's not going to make any difference. The only thing that's going to matter is counting the number of the negative factors. And whenever that number is even, the overall result will be positive. So of course we know the rest is just going to be the same as 2 to the power of 4, so we'll get 16. And of course, for a final answer, we don't include the plus because the simplest form of positive 16 is simply 16. We write it like that. Now in this next one, the base is not going to be -2. This is an error some students make. Here, the only number being raised to the power of 4 is the 2. The negative is just going to carry like a factor. So here, remember the base here is going to be 2 again, and the exponent is 4. So here, the negative can be interpreted in this way. You can think of this as -1 times 2 to the 4. That's a good way of seeing it. So basically, it's going to be -1 times 2 times 2 times 2 times 2. So we already know what this part is. We've done it twice. That's just 16. So it's going to be -16 this time. So for our next example, we just have one extra factor. So we get 2 times 2 times 2 times 2 times 2. So we know up to here we have 16 times another 2. That will give us 32. So here we're going to use -2 as a factor 5 times in a product. So now this time, because the total number of negative factors is odd, because it's 5, we know that that's always going to generate a negative result. So we're going to get negative. Now we know up to here, we know that 2 to the 5 is going to be 32. So we get -32 as our final result there. So here in the next one, the negative is not going to be raised to the power of 5. So the base here is only 2. Here the base was -2. Here again it's only 2. So negative will just carry, and we'll have 5 factors of 2 like that. So we're going to get -32. So notice here, while we had a difference in the results when the exponent was even, we don't have the same situation here when the exponent is odd. Both of these will generate a negative result. So it's good to note that in general, when you have a negative number that's raised to an even positive integer, the outcome is going to be a positive result. And when you have a negative number that's raised to an odd positive integer, the outcome is going to be a negative result. In particular, it's interesting to look at -1 as the base. -1 raised to any even positive integer is going to generate 1. And -1 raised to any odd positive integer is going to give us -1. So if we have something like -1 to the power of 100, we don't need to sit here and think about this a whole lot, because we know this is going to end up being 1. And if we have -1 to the power of 2003, there's no need for us to write -1 2003 times and multiply. We know this outcome is just going to be -1. Now, you may have seen some people who are very impressive in mathematics classes. When they're offline, they yell out the answers all the time. It's not that they know a whole lot more than you do. It's just that there are a few key things that they memorize and they have saved up in their minds, so that when they need to, they call on them, and that way they don't have to just keep jumping to a calculator for simple results. So it's extremely useful to know these tables that I've listed here for you. So here we have a table of squares, cubes, fourth powers, fifth powers, and sixth powers. Notice they get increasingly smaller because these numbers are going to get quite large and rather difficult to remember. So, but this is completely sufficient, and this will in itself make you much sharper with this material. And also later on when we study radicals, we realize these tables have a dual purpose. When you go from left to right, you're raising to the power. When you go from right to left, you're taking a root. So for example, 2 to the power of 2 is 4. And we also know that the square root of 4 is 2. Well, the positive square root of 4. So these are going to have a dual purpose for us later on. So one way, for example, we can say 3 to the 5 is 243, or we can say the fifth root of 243 is 3. So make sure that you memorize these tables, because more than just being sharp and quick, what's going to happen is when we need to recognize some of these powers in some of our problems, it's extremely important to be able to do that just naturally without having to resort to calculators, because it would make matters much more efficient if we can handle them without a calculator, as you will see throughout the course. So here we're just going to memorize a few tables, and that's going to take us all the way to the end of the course as far as these things are concerned. All right, so here we have some powers to evaluate, and now the first one, for instance, we have -5 to the power of 4. Now we know that we have a negative number raised to an even power, so we can deal with the sign right away and be done with it. We know this is going to end up being positive, so we just need to worry about 5 to the 4. And if you recall from the table, it's 625, and if you don't, it's not that difficult just to calculate it. So we know this is 25 times another 25, and that is 625. All right, so for our next problem, -2/3 cubed, we know the outcome is going to be negative because we have a negative number raised to an odd power. So what we're going to do is just start with a negative, be done with the sign. We always want to take care of the sign so we don't forget it. So then we just have 2/3 times 2/3 times 2/3, which is, of course, as you can see, is going to be -2 cubed over 3 cubed. So in the future, we'll just jump to this right away. And we end up with -8 over 27. And that's all we need there. Here we have -4 to the 4. So this negative is not even being raised to the power of 4. So it's just going to carry. And 4 to the power of 4, if you recall from the table, is going to be 256. So here we have a product of two powers, so we can just take care of each and go ahead and multiply it out. So we get 3 squared, which is 9, times 3 cubed, which is 27. And when we multiply that out, we get 243. Or we could have realized that 3 squared times 3 cubed, that means 3 times 3 and then 3 more factors. So that's actually 3 to the 5. And we have that in our table. We know that that's 243. So here for the next one, we'll just go with the order of operations and take care of what's inside the parentheses first. So that's going to be 9 squared, which is 81. So now we arrive at our first law of exponents that we're going to study. We can either say law of exponents or rule of exponents, makes no difference. And that is the product rule for exponents. So we're going to explore that. Basically, we want to know what happens if we multiply two powers such as we see down here, which happen to have the same base. The exponents may or may not be equal, it doesn't matter. So as a motivation for how the rule works, we look at an example here. Let's say we look at 2 cubed times 2 squared. Now we know that 2 cubed means 2 times 2 times 2, and that's 3 factors of 2. And 2 squared means 2 times 2. So we notice that we end up with a total of 5 factors of 2. So 2 to the 5. Notice we could have arrived at that by just adding those two exponents. What do we do with the 2? We just carry it. We keep it. So we get 2 to the power of 3 plus 2, which is 2 to the 5, which is 32. Now we can generalize the rule. We can say, when you multiply two powers like this, x to the m times x to the n, we keep the base, and you will see, with the exception of one case where the base actually disappears, and that's x to the 0, which happens to give us 1. For all other rules of exponents, the base remains and it does not change. So the base is very stable in that sense when it comes to these rules. All right, so when you multiply two powers with the same base, keep the base, add the exponents. And some people erroneously, because of this, call this the sum rule. This is actually not called the sum rule because it has to do with what you're doing with two powers, and that's multiplying them. So that's why it's called the product rule. Now, it's always good to remember such rules in words, because you'll activate a different part of your brain and you will remember it more easily if you have it both symbolically as well as in words. So in words, to multiply two powers with the same base, keep the common base and add the exponents. Here I just want to warn you that a lot of students incorrectly multiply the exponents because of the name of the rule. So they see x cubed times x squared and they go, okay, so that's x to the 6. And of course, that's completely wrong. You do not multiply those exponents. When you multiply two powers with the same base, you keep the common base and you add the exponents. Actually, probably a better name for the rule would have been the product rule for powers. But we've kind of like started with exponents and everybody uses that name for the rule, so we'll just stay with it. But that's what's going on here. Let's see if we can apply this rule we just learned in a few cases. So here we notice that we are multiplying two powers with the same base. Whenever that's the case, we can apply the power rule, the product rule, so which we know is x to the m times x to the n equals x to the m plus n. So here we notice that the exponent is that invisible 1, right? So there's always an exponent. If it's not written, then it's 1, okay? So here we're just going to get 5 to the power of 1 plus 3. So we get 5 to the power of 4. We've seen that before. That's 25 times 25, so 625. For the next one, again, we notice that we have two powers that we're multiplying and they have the same base. So we go ahead and keep the common base and we add the exponents. So we end up with 2 to the 5, which, if you recall from our first table, is going to be, I meant first set of tables that we looked at, it's going to be 2 to the 5, which is 32. Now, can we use it here? Of course, the rule never said the base has to be positive. This works for any base. So here we do have a situation where we're multiplying two powers with the same base. Therefore, we can use the same rule. So we're going to keep the base and we're going to add the exponents. So we get 2 plus 2. So we get negative 4 to the power of 4. And here we have a negative number raised to an even exponent. We know the answer is going to be positive. So we just need to worry about what 4 to the 4 is. Again, we've seen that. We know that's 256. And we don't need to write the plus for the final answer. All right. How about here? Sure, why not? It doesn't matter that they're fractions. These are two powers that are being multiplied and they have the same base. The base is 1/2 for both of them. So yes, we can apply the product rule. So we get 1/2, keep the common base, add the exponents. So we get that. So we get 1/2 to the power of 6. So we know that's going to end up being 1/2 times 1/2, etc. So we're going to get 1 to the 6 over 2 to the 6. So that's going to be 1, of course, because we know any power of 1 is just 1. And 2 to the 6 is going to be 64. You really, really want to know those tables that I showed you earlier. They're going to save you so much time, make you so sharp with this material. All right, so can we use the product rule here? Well, of course not, because obviously this is not a product. Yeah, we have two powers that happen to have the same base, but the problem is we are not multiplying them. So what do we do in a situation like this? Do we just do nothing? No, you can still evaluate it. You just take care of them one at a time. You take care of 3 squared, which is 9, plus, and you take care of 3 to the 4, which, if you know your table, you know is 81. So we get 9 plus 81, which is 90. So yeah, there's something we can do. We just can't use this rule because we don't have the conditions for using that rule. How about here? Yeah, we're multiplying two powers, but remember, the rule doesn't say when you want to multiply any two powers, you can do this. It says the two powers have to have the same base, right? Do they have the same base here? What do you think? That's right, they don't. So what do? Again, we can do something, but like this one, we'll just take care of each of these separately, then multiply. So 2 cubed, you should know by now, is 8, and 3 squared is 9. So we just get 8 times 9, which is 72. As we do these, make sure that you can clear each screen on your own without looking at the work before you proceed. That's how we learn mathematics, by doing it. Okay, so now we'll do the same thing we've been doing, but we'll go ahead and bring in some variables. And they behave in exactly the same way. So here we have two powers. They happen to have the same base, and we're multiplying them. That means we can use the product rule, which is x to the m times x to the n equals x to the m plus n. You want a very easy way to learn your formulas? Every time you apply a formula, write it down first. Guess what? You do that after, 5, 6, 7 problems, you're going to have it fully memorized. All right, so, but more importantly, that's why I gave you the motivational problem before I actually state the rule. The best way to make sure you're going to remember something is to understand it. Because once you understand something, it's just not going away. For some reason, that just gets completely solidified in the brain, and it will stay in there for the long run. All right. Now, so here we're just going to get x to the power of 2 plus 5, which is x to the 7. All right, so for this next one, we're multiplying 3 powers and they have the same rules. So we can take care of it 2 at a time, multiply these two, get an answer, and then multiply by that. Or we can realize this is just going to work out nicely by just writing the base and adding all those exponents. So let me show it both ways. So if you do it in 2 steps, you're going to multiply the first 2. That's going to give you u to the 7, and then multiply by u to the 5. So you're still going to end up by adding 7 and 5 to get u to the 12. But normally when we get something like this, we just go one shot. We just go 3 plus 4 plus 5, like that, which is of course going to give us the same thing, but in a more efficient manner. All right, so now here we're multiplying these two expressions, and the way to deal with this is very easy. Just go ahead and multiply the numbers. 2 times 3, that's going to give us 6, and we go ahead and multiply c squared and c to the 7th using the product rule. So that gives us c to the power of 2 plus 7, which is 9. Now the reason we can do this is, of course, the commutative and associative properties of multiplication, because what we're saying is that if we have 2c squared times 3c to the 7, we're saying we can go ahead and switch the order here and put c squared times 2 times 3, like that, times c to the 7. Then we multiply those and we get c squared times 6 times c to the 7. And then we can switch the order of c squared and 6 again. So we get this. So we get 6c to the 9. So we're taking a lot of basic mathematical steps for granted when we jump from this to this, but this in essence is the justification for why we can do something like that. And do you normally have to show all that? No, you don't. We can just basically go to this, but it's good to know. All right, in case you decide to get into proving mathematical statements at some point, theorems, this is the kind of thinking process you need to be comfortable with. All right, so here we notice that the variable parts do all have the same base, so we should be able to use the product rule, but we'll go ahead and multiply these coefficients first. So we have -1/2 times 2/3 times 9. If you want to write it as 9/1, you can, so you make it look like the others, a fraction. And we're going to get x to the power of, we're going to add those exponents, 3 plus 4 plus 11. All right, so now when it comes to the multiplication of these 3 fractions, we know that we can cancel from any numerator to any denominator as long as the only operation involved is multiplication. So We'll go ahead and do that. We'll go ahead and cancel these. That leaves us 1 and 1, and these two leave us 1 and 3. So we notice that, first of all, we'll deal with the sign in the next step. We have one negative factor, so, and that's an odd number, so we know the outcome is going to be negative. Now, as far as numbers, we only have a 3 left on the top, which is going to matter because 3 times 1 is just 3 times another one. It's still 3. So we're going to get 3, and the denominator all became, they all became 1, the denominators. So we just get negative 3. And then x to the power of 3 plus 4 is 7 plus 11 is 18. All right, remember the drill. Always, when we get to a new screen, always try to pause the video. Try to get them on your own before you continue watching. That's the most powerful way of actively engaging yourself in the learning process. All right, so in this next one, we're going to multiply the numbers. Notice we have 1, 2, 3 negative factors. We know the outcome is going to be negative. Let's get that out of the way. And here we're going to multiply 3 by 7 by 2. So of course we know 3 times 2 is 6 times 7 will give us 42. And then P is the common base, so we keep it. And we go ahead and add the exponents. So 2 plus 7 is 9 plus 3 is 12. And that's it. We have now multiplied that out. How about this relatively complicated looking thing? Can we apply the product rule here? Of course. You're multiplying two powers, right? Each of these is called a power, and they have the same base. Yes, the base is not super simple, but they have the same base. That's the base. So we're just going to keep the common base, and we're going to add the exponents. 4 plus 6, we know that is 10. And that's all we have to do. Now, you don't want to sit here and do anything else with this at this point, because this is a much more complex outcome than you would imagine. So we're not ready to deal with something like this yet, but we will at some point be able to handle that, just not yet. For now, we just leave it as is. Next, we want to look at how to handle a power of a power, and that is managed by a rule called the power rule for exponents, which we'll look at next. As always, we'll do a little bit of a motivational problem first. Let's say we want to look at 2 cubed squared, right? So this is what I mean by a power of a power. So we notice that 2 cubed squared by definition just means write 2 cubed twice and multiply, right? That's just by definition of an exponent, or a definition of exponentiation. And here we know that we have a product of 2 powers with the same base, so we can go ahead and apply the product rule now. So we get 2 to the power of 3 plus 3, which of course 3 plus 3, it can be written as 3 times 2, so we get 2 to the 6. So it looks like when we have a power of a power, we can keep the base and we can multiply the two exponents involved. So that's exactly how it works out. And of course, 2 to the 6 is 72. So if we generalize that, if I have x to the m and the whole thing is raised to the power of n, I just keep the base. We don't need to say common base here because we only have one base we're dealing with. So we just keep the base and we multiply those two exponents. That's when you multiply exponents for the power rule. All right. So in words, to find the power of a power, keep the base and multiply the exponents. So let's see if the power rule applies to these. Let's remember what it is. So we have x to the m raised to the n, and that's going to equal to x to the m n. That's m times n. So here we do have a power of a power, so we can apply it. So we're going to keep the 4, and we're going to multiply those 2's. So we get 4 to the power of 4, which is a problem that keeps popping up for us for some reason. And we end up with 256. I'm sure you know that by now. We've seen 4 to the 4 a few times. All right, so here we have 2 to the 4, and then the whole thing raised to the power of 5. So yes, it's a power rule situation, so we can apply the rule. So we get 2 to the power of 4 times 5, which is 2 to the power of 20. Now, be careful and don't try to do this in your head. This is not, well, unless you are one of those people who can do that. I can't. But anyway, this is a really large number. Okay, so at this point, a lot of the times in systems like MyMathLab or textbooks, they'll just ask you to leave the answer in exponential form. So this would be the answer. But if they actually want it worked out, then you can utilize a calculator for that. All right, so here we'll utilize the help of this nice HP Prime graphing calculator, which is, by the way, available for free. We won't be using anything like this in our classes. We'll be using a different calculator, which will be described through emails, but this is also nice to have on computers as well. So here we're going to start with 2, and we're going to raise it to the power of 20. And you notice it's quite a large number, 1,048,576. All right. So be careful with something like that. It's, again, especially when people first learn about exponents, it's easy to make the mistake of wanting to multiply those. But remember, you never multiply a base by an exponent. All right. Not unless we get something like a logarithm involved, which will not be coming for quite some time. Even in that case, it's with some special skills which we'll acquire at that point. Okay, so but generally speaking, the safest thing to remember is there is no scenario in which you're going to multiply a base and an exponent. Remember that. All right, so here our inner base is -2. So we're going to write that, and we're going to multiply the 3 and 2. So 3 times 2 is 6. So we get -2 to the power of 6, or the 6th power of -2. Now, since we have a negative number that's raised to an even exponent, we're going to get a positive result. And we just need to worry about what 2 to the 6 is now. So we know that 2 to the 6 is 64 because we have memorized our tables. So we know that that's going to be 64. And of course, we don't need the positive sign in the final answer. Again, here, yes, we have a power of a power. So yes, we can use the power rule. So here we're going to get 1/2 to the power of 3 times 4, which is 12. Remember, that's going to be 1 to the power of 12 over 2 to the power of 12. The top is easy to calculate, that's just 1. But 2 to the power of 12, remember, again, is not a very simple small number. So 2 to the power of 12, 4096. So we get 1 over 4096. Now, if they ask you to leave the answer in exponential form, just write it as 1 over 2 to the 12, like that. All right, so here we have negative 0.1 squared squared. So that means negative 0.1 is our base. So we write that, and we multiply the two exponents, which are both 2's as well. So we get 2 times 2, which is 4. Now this, you should be able to do without a calculator. First of all, sign-wise, we know that we have an even power of a negative number. So we know the answer is going to be positive. Now remember, one easy way of dealing with this is just to think of that as 1 over 10. So we're just looking at 1 over 10 to the power of 4. So that's 1 to the 4, which is 1 over 10 to the 4. Of course, we know that 10 to the 4 is a 1 followed by that many zeros. Like so, okay? So 1 over 10,000. So, or you can go back to decimal form if you like for your answer, like so. Remember that when you go from this kind of a fraction to decimal, the number of zeros here you get before 1 is going to be 1 less than the number of zeros here. Here we had 4, so when we go to this format, we're going to get 3 zeros there, okay? All right, so that's that. So now we're going to basically just do the same thing, but with variables involved. So these in fact can tend to be easier because there's no real computation that you need to do right away. So here we just get x as the base. Remember the rule, x to the m to the n equals x to the m times n. So here we're going to get x to the power of 2 times 20, which is 40, and that's it. So here for the next one, the base is going to be 1 over u. So we're going to write the base, and we're going to multiply the exponents. So 3 times 4 will give us 12, and we end up with 1 to the 12, which is of course 1 over u to the 12. And that's pretty much all we can do there. For the next one, we have a negative number raised to an odd power, so we know the answer is going to be negative. And here we're just going to apply the power rule to u, so we get u to the power of 2 times 5, which is 10. So for this one, we know we're just going to get 100 factors of a over b. So that's just going to give us a to the 100 over b to the 100. Now, the only way this could really be related to this rule at all is we think of this as a over b to the power of 1 and then raised to the power of 100. So I'm not sure what I was thinking when I put this example here, but anyway, this is how it's done. We'll just let it be. Now, the power rule, which in simplest form we know is x to the m to the n equals x to the mn, has a couple of relatives which are a little bit more complex, and that is what happens if instead of just one power being raised to the power of n, you have a product of two different powers raised to some exponent, some power. So the answer is very simple. Just apply the power rule to each. So here you'll just get x to the mc times y to the nc. Remember, this only works if the operation here is multiplication. Do not ever do this if the operation is anything other than multiplication, such as addition, subtraction. Even if it's division, you want to make first sure turn it into a multiplication and then proceed. But that's how you do that. And then here, what happens if you have a power of a quotient of two powers? Same business. Take care of the power rule on the top, so we get x to the mc over y to the nc. And that's how you handle those more complex situations. Let's take a look at a couple of examples. All right, so here, notice that we need to start paying attention to the order of operations. So we're going to go ahead and take care of this and this separately, and then we'll multiply. Notice we can't apply the product rule or anything like that because these two bases are different. So just applying the power rule in this expression, we get 2 to the power of 3. Remember, there's always an invisible 1, and when you multiply 1 times 3, you just get 3 anyway. So we end up with 2 cubed x to the power of 6. Now, I want to warn you, a lot of people, they never forget the x, power, having to, use the product rule. It's the numbers they forget. Remember, every factor in here you need to raise to the power of 3. That includes the 2 itself. That's why we get 2 cubed times x to the 6. Now we apply the power rule here, so that means every factor is going to get squared. So we get times 4 squared x to the, remember the rule, you need to multiply those. So x to the 8. So we know that's 8, and we know that that is 16. So we get 8 times 16 x to the power of, now we're going to apply the product rule because we're multiplying two powers with the same base. Let's remember that x to the m times x to the n, remember, equals x to the m plus n. So we get 6 plus 8, which is 14. So we just need to take care of 8 times 16. Now, we know that 8 times 10 is 80, and 8 times 6 is 48. So 80 plus 48 should give us 128 x to the 14. Definitely try these on your own before you continue watching. That's really effective doing it that way. All right, assuming you have come back after your own attempts, I do have a parenthesis here. You can see the corner of it that has gotten cut out by my screen recording rectangle, but it's there. All right, so this opens with a parenthesis like this. All right, so now we're going to apply the power rule to, in other words, raise each factor here to the power of 2, starting with -3. Now we know that -3 squared, that's a negative number raised to an even power, so it's going to become +9. Now u to the power of 2 times 2. So that's going to be u to the power of 4. V, what's the exponent of v? 1. So we multiply 1 by 2. What do we get? We get 2 times. Now here -2 is being raised to the power of 3. A negative number raised to an odd exponent, that's going to be a negative answer. So I'm going to need a parenthesis here. -8. 2 cubed is 8, and the negative means it's going to be a negative result. U to the power of 3 times 3, right? So what is that? That's u to the 9. V to the power of 5 times 3, so that's v to the 15. So now we're just going to multiply this -8 and that 9 to give us -72. And then u to the 4 can be multiplied by u to the 9 to give us u to the, remember, product rule. So u to the power of 4 plus 9, which is 13. So u to the 13. And then v, again, these two can be multiplied because they're two powers with the same base. So we can apply the product rule. So we get 2 plus 15, which is 17. And that's it. That's all we need to do there. All right, so for this next one, remember, we don't want to let fractions scare us. They're handled exactly the same way. So here we're going to square -2/3. If you're not comfortable with fractions, write it down. It's not a big deal, like that. And then x to the power of 5 times 2, so we know that's 10 times. Here we have -1/2, which we're going to cube. And then x to the power of 4 times 3, which is 12. One of the key things is that when you try one of these problems and you don't come up with the correct answer, for example, if you're using my math lab, it tells you, hey, that's not right. Don't give up. I mean, the key is to persevere. That's the only way you're going to become really, really strong in mathematics. If you just try something once and it doesn't work out and you give up, there's not going to be quick progress made. So make sure you don't give up just because you don't get the right answer the first time. All right, so here we have a negative number and we have the second power of that negative number. So we know the answer is going to, the outcome there is going to be positive. 2 squared is 4, 3 squared is 9. So we get 4/9 times, let's go ahead and take care of this real quickly, -1/2 cubed. Now the third power of a negative number, we know is going to be negative. And 1 cube is just 1. 2 cubed is 8. Okay, so we're finished with the numbers. So here we have two powers that are being multiplied and they have the same base. So we can use the product rule. So we get x to the power of 10 plus 12. And now we're just going to clean it up and wrap it up. So we notice that the golden rule of multiplying fractions tells you what? Always simplify before you multiply. All right, I was being lazy here. So first of all, notice that you have 4 here, 8 here. Because it's multiplication, you can cross cancel. Remember, from any numerator to any denominator, as long as you're only multiplying. So 4 and 8 will leave us 1 and 2, and that's that. So there's no more simplification possible. So now we multiply across. First, we notice we have positive times negative, so the sign will be negative. On the top, we only have 1 times 1, which is 1. Downstairs, we have 9 times 2, which is 18. And then x to the power of 10 plus 12, which is 22. And that's how you do a problem like that. So anytime that time allows you, double check, make sure you've done it correctly. So here we have negative 2/3 squared times x to the power of 5 times 2. Make sure you don't make the relatively common error of squaring the 5. That's not how the rule works. The rule says if you have a power and then you want to calculate a higher power of that power, you keep the base and you multiply the exponents. We saw earlier through the motivational example why that is so. So go back in the video and find out why if you need to. But we don't raise m to the power of n, we multiply m and n, okay? So that's how we got x to the 10, and then here we have negative 1/2 cubed times x to the 12. This is going to give us a positive 4/9. This is going to give us a negative 1 cubed, which is 1, 2 cubed, which is 8. Then we multiplied, but before we did the multiplication, we remembered the golden rule of multiplying fractions, which is always to simplify, meaning any possible cross-canceling before you multiply across, okay? So here we end up with negative 1 over 9 times 2, which is 18, and then x to the 22. Notice if you didn't cross-cancel, you would have had negative 4 over 72. Yeah, I mean, you could sit here and start reducing this and eventually get to negative 1 over 18. But why would you want to have to do that when you could have done this and avoided doing it? See, always be efficient. Many students I've noticed who hate mathematics, it's because they're not efficient in it. Because so they end up having to do a lot of busy work. So if you become efficient, you skip the busy work and you may actually start enjoying mathematics. All right, so for this example here, we notice that we have a quotient, so we're going to raise every factor within this quotient to the power of 4. We don't miss anything, right? So we start with 3. It's if you become really systematic about this, it's extremely simple. But you have to just do enough of these till they become comfortable for you. So 3 to the 4, k to the power of 3 times 4. So what is that? That's it, 12. M to the power of 2 times 4, right? So what is that? 8. Over 2 to the power of 4. Some people miss these because they're down here. Don't let the distance throw you. All right, so we get 2 to the power of 4. N to the power of 4 times 4, which is what? You said it, 16. P to the power of 5 times 4, which is what? Exactly, 20. All right, so notice how easy that was. Now we're just going to get 3 to the 4, which is 81, k to the 12, m to the 8, over 2 to the 4, which is, as you know, 16. N to the 16, p to the 20. And there is no cross-canceling possible. 81 and 16 only have 1 as a common factor, so we don't really get any simplification out of that. And that's it. So there you go. Make sure you can handle these on your own before you proceed to our last example for this video. All right, for this problem, we're going to do a little bit of an application. We want to find the area of this depicted triangle. We know that in a right triangle, the two legs can play the role of the base and the height. So we have this, which we can treat like the base, and we have this, which we can treat like the height, or the other way around, makes no difference. So here we have, whenever you have an application which is geometric in nature, start by writing down the formula. Don't plug anything in, just write down the formula. We know that the area of a triangle is 1/2 base times height, okay? And notice that you can also write this as base times height divided by 2. Sometimes this is a more efficient format to use. In fact, I'm going to use that format here. So I'm going to get A equals, for B, I'm going to plug in 4x to the 5. We can leave the units out for the time being, or you can bring the units in as well. Let's bring them in so you can see how the units work out. So we get 4x to the 5 feet times the height, which is 3x cubed feet, and then over 2. So we do notice that we can cross cancel 2 and 4 to give us 2, and of course we can do that because there's only multiplication going on either on the top or the bottom. If there's even a single addition or subtraction either on the top or on the bottom, you can't cross cancel anymore. But as long as you only have factors both in the numerator as well as in the denominator, then it's safe to cross cancel. So we get 1, and now we're going to get 2 times 3, which is 6, and then the x to the 5 times x cubed we can handle using the product rule. So we keep the base, add the exponents, so we get x to the 8, and then notice foot times foot turns into foot squared, which makes sense because, as we know, areas have square units, and you can see it works out here as well. You always have to make sure your units work out. If the units don't work out, there's something wrong with the formula. All right, and that should do it. So anyway, make sure you practice these and do more through the homework system, and that should do it for this particular video. Stay safe until our next video.